Hey guys, so yeah, as it's been already helpfully pointed out, I'm Alexander. Well, Alex is short for Alexander. That's sometimes a mistake what it stands for. I work in Adform, so one of the sponsors of this conference. And yeah, so basically my day job is data engineering in Scala, but I also have like a hobby in my spare time. I'm interested in formal logic and verification and proof systems. So I dabble with systems with programming languages or proof assistants like Idris or reddict. So today I'm gonna present this talk. It's gonna feature some code in Idris. So I guess let's go. So there'll be like roughly 5 parts to this talk. The intro to proof theory and logic in general, lambda calculus, abstract machines for lambda calculus, control, and sequent calculus, the namesake of the presentation. So let's get started with the first part. So the common theme of this talk, if we would summarize it in 1 or 2 words, would be proof theory. So what is historically a proof theory? A short introduction. It's a branch of mathematical logic, and mathematical logic by itself kind of coalesced, appeared in the I think in the half of the 19th century. And the idea was that at that time there was like lots of branches of mathematics, and people started thinking what if like some branches are actually like false at their core, and like how can we verify, like for example, that if we are doing calculus, we're not just like doing some abstract stuff that has no relation to the truth. And so there was these mathematical questions, like if mathematics is itself consistent. So there was this guy, David Hilbert. He kind of began the whole field of proof theory, and the origin of it was that. It appeared, he introduced it in the 1920s, and the idea was that you could extract like a small core of all mathematics, so like this mathematical logical core, some kind of finite system, and then you should prove this consistency of this system like by hand and paper, so it should be like simple enough to verify that it's actually consistent, and then using the system kind of verify that all the rest of the mathematics is consistent. Unfortunately, this was not to be, and there was this guy, Kurt Gödel, who actually worked on this Hilbert's program, and in the process he discovered his famous incompleteness theorems, which, to put it simply, say that any such small finite system would be either insufficient for the task or it would be inconsistent itself. But still, proof theory kind of thrived on, and this study. So basically, it turned to studying like these small formal systems in general, and figuring out which properties they have and how can they translate to the process of proving and stuff like that. And it's quite a fruitful field. It has lots of subfields. So, well, we're in a programming conference. So, why is it interesting for programming? There are basically 2 main applications how this can be relevant to programming. So one is this so-called paradigm as a normalization as computation, or cut elimination as computation. This basically says that this basically corresponds to functional programming, and that means that you have your program as a proof, and you try to simplify it until you arrive at some kind of answer. And the other branch or way of applying it to computation is this proof search as a computation. So then your program state is some kind of a proof that you want to generate, and this basically corresponds to logical programming. So if you have some kind of set of constraints, how you can generate some kind of statement that satisfies these things. Yeah, so for doing these proof theory, so to study these things, like this study of these frameworks, is called, it's like a subfield of proof theory. It's called structural proof theory, and there are 3 kind of frameworks or general ways to do it. So one was introduced by this David Hilbert guy, so it's called this Hilbert axiomatic system. So the idea is that you have a bunch of axioms and a single rule, which is so-called modus ponens, which basically says that if A and from A follows B, then B. Yeah? So you plug like the A into the like this implication, and you arrive at the conclusion. But if you use like this system natively, this corresponds, if you've seen this in programming, to this called SKI combinator kind of style thing. And it's kind of impossible to do. It's very verbose. It's very hard to actually figure out any proofs or write any programs this style. So usually people use one of these two systems, like the second or the third. They were both introduced by this guy, Gerhard Gentzen, in the 30s, and they're called natural deduction and sequent calculus. How are they defined? Like what do they consist of? So you probably have heard this thing called Curry-Howard correspondence or isomorphism or whatever. So very simply it says that a theorem in mathematics, like if you interpret it constructively, it corresponds to a type of some program, and then the proof is the term or the body of that program. So basically the proof theory is then the study of these programs, their bodies. So if you write this logically, like on paper, these proofs then are usually written as like chains of applications of some kind of rules. And these rules, the basic building block of such a rule is called a sequent. So the sequent is this thing. So you probably have seen, I guess, it today in several talks. So what does this thing mean? So this means that you have a bunch of formulas, some kind of statements or types on the left, and you have this turnstile symbol, and then a bunch of statements on the right. And like intuitively, this means that if all of these statements are true, then one of these statements must be true. So that's basically it. That's just a syntactic sugar for this idea. Usually, like when you do functional programming, like when you do systems which corresponds to functional languages, you constrain this right-hand side to there should be like strictly one formula. So it means like given all of these things should be true. And then a rule consists, is usually written as this bar. So on top of the bar you have like sequence that you start from, and this is the sequence you should arrive at like after applying the rule. So for example, if from A and B follows C, and from A and B follows D, then from A and D follows C conjunction D, right? So both of these should be true. So usually you can have, as I said, like arbitrary amount of these formulas here. So usually people lump them into some kind of a structure. So usually it's a set or a list. Or a list like should behave as a set, but that's a technicality. And they denote it with a capital Greek number, so like gamma or delta. So what is a natural deduction then? So it's like this very simple system. It corresponds to this so-called minimal propositional logic. So the only logical connective in this system is the implication or the function in the programming parlance. And it has like these three rules, these axioms. So if on the left-hand side of the sequence you have some A, then from gamma follows A. If introduction of this implication, if there's A and gamma from this follows B, then from gamma follows that from A follows B. So basically just moving it to the other side of the sequence. And elimination. So how can you make this implication or function, and how you can destroy it or eliminate it. So what does this have to do with functional programming? Let's take a look at lambda calculus. I think if you've been today to the talks, there were already a couple of talks explaining this, so I probably won't go into detail to save time. But basically there are these three constructors, and there's this rule for reduction, which is usually called beta reduction. So if you apply something to a lambda, you substitute in the body for the x, the argument for x. Usually when implementing this, instead of names, people use this so-called de Bruijn indices. So this is a notation which there was this Dutch mathematician, Nicolas de Bruijn, came up with. So intuitively it corresponds that you remove the argument names from lambdas, and in the bodies, instead of the names, you have a reference to how many lambdas ago this was introduced. So like a symbol identity function becomes just lambda 0 because it was like immediately introduced and then immediately referenced to. A function that applies an argument to itself would be like lambda 0, 0. A function that like ignores x and then introduces y is like lambda 0 because y is immediately introduced here. The other way around would be lambda 1 because you skip over one lambda and so on. So I guess you can figure out the idea. So you just count to the left how many lambdas you've skipped since the introduction, and just put this number instead of this name. So the system is kind of hard for humans to read, but good for computers too. So if you're going to implement this, this is the easier way. Let's have some first Idris snippets. So this is how you would declare data types. So this is, for example, these numbers that we would use for this indices. So we would use natural numbers. This is just unary numbers So a unary number is either a 0 or a number plus 1, a successor, right? Not very hard. So this is how you define a data type. Simple data type. A list would be like a type constructor, so it's like either an empty list or something prepended to another list, right? So just two cases as well. So then how would you write this untyped lambda calculus in Idris? It's just like these three cases. Either it's a variable with this natural number, or a lambda constructor that wraps over a term, or an application of a term to a term. And this is how you would encode like this, for example, simple lambda terms. Just application of lambda to vars and so on. Okay, I guess this is kind of straightforward. So how we would reduce this? Yeah, I guess this was also kind of talked about today, but basically, like you substitute the blue thing inside the green thing, like for the places denoted by the red thing. So basically, instead of x's here, you substitute this argument, and then you reduce this in 2 steps. And for this function, so like the kind of important or the interesting thing in here is to notice that this pattern, like which you apply this reduction to, is called the redex, and the peculiarity of this lambda calculus is this redex is not always on the top level. So you may have to search arbitrarily deep into your lambda term to find like this pattern, this redex to apply your stuff, your reduction to. So like if you write an interpreter for lambda calculus, it would be basically non-tail recursive. It would, for example, if it would search for an application, it would have to split the search for like both sides of application. So it then becomes like an arbitrary recursive function. Okay, let's do something more interesting, the simply typed lambda calculus. But first, let's see how we could encode the so-called list membership. So a list membership, so this is where like the property of Idris being a dependently typed language comes in. So this, for example, this proof of that some kind of A is inside of a list of A is a pointer to where it is. So and then a variable, a member is either at the head, so it's like here, it's explicitly at the head of some list, or if it's in X is in some element XS, then it's somewhere there. It's also in the list where you have some Y, which is like not equal to X. So either it's in the head or it's somewhere in the tail, and then you recursively can find out so where it is. So if you kind of squint, then this thing is just like a fancy rephrasing of natural numbers. So here is just a 0, right? It's like a 0th position, and there is just a successor of this recursive call. So if it's like in the 2nd position, it would be like there, here, and the 3rd would be there, here. And so basically, this function kind of erases these fancy indices, saying like that this is not just a number, but like an actual proof that of this specific element being in this specific list. But you can think of them as just numbers. So how we would encode a simply typed lambda calculus? Well, you have to, I hope everyone can see this, but you just you introduce a structure for types. So it's either like some kind of base type, or it's an arrow type or an implication between 2 other types, which can be recursive as well. So this is just some synonym, this squiggly arrow. So it looks more readable. And then you have these same 3 things, but then your term now is indexed with these contexts and these types. And the context is just a list of types of free variables. So then the var thing is then if you give it like a proof that your element is inside this G, then it's a term of type A with the context of G and so forth with lambda. So lambda kind of pops off the top, the 0th element in the context and forces it to like appear in the type, and the application does kind of the opposite. So if you have a function and an argument, then it kind of applies. So for example, if you have this kind of identity type, so for our previous examples, we had these 3 terms. The first one is actually not typable in simply typed lambda calculus because there is no such type that can be applied to itself, right? It would be like an infinite recursion. So only like terms 2 and 3 are typable, but essentially the same. You just replace these numbers with these kind of so-called structural proofs where in the context are these types. And as you've seen it, both of these reduce to this identity function. Well, actually all 3 of them do. So, this is kind of the property, this is called, I think, subject reduction, but basically it says that the terms with the type, with the kind of some kind of type should reduce to the term with the same type, which makes sense, right? You don't want to evaluate like 1 plus 2 and get a string, which I guess you can in some languages, but whatever. And kind of not very a big surprise, but actually simple type lambda calculus is the same thing literally as natural deduction. Like if you just look at these rules, what we did, we translated these proofs into these constructive data structures, and all of these things are like literally the same. So this is A prepended to G of type B, and so on and so forth. So this was discovered by William Howard, so the same guy who appears in this Curry-Howard correspondence. And yeah, so basically this simple type lambda calculus is the same thing as this minimal propositional logic. So as I said before, if you would write an interpreter for lambda calculus, then it would be not tail recursive. It would have to like heap things on stack indefinitely. So what if you wanted to write a tail recursive, like a deterministic interpreter for lambda calculus? So these things are usually used when you try to write like a compiler for a functional language, and they are called abstract machines. So abstract machine is basically the same as a virtual machine, but a virtual machine is something that has an actual implementation. And if it exists on paper, then it's an abstract machine. But the idea is like it's like a virtual machine, which is very simple and easy to study on paper. So yeah, it's a tail recursive interpreter. Usually it consists of three parts: the control, or the actual term that you're reducing at the moment, the so-called closure or environment. So basically some kind of data structure which holds the references of what the variables refer to, basically, and some kind of stack or a continuation. So this is the part that makes this interpreter tail recursive. It's like the remainder of the computation. So what should you do once you've reduced the thing under control? So this is kind of hand-wavy. So we'll for now look at the simplified version. So you can, if you have this native substitution function, so you define it somehow. We won't really look at how, but it doesn't really matter. Then the kind of the essence of the abstract machine is just these two things. It's a control and a stack. If you have this substitution. So this is how you define like an archetypical KRIVINE abstract machine. So it's a machine which kind of does these naive, lazy, or call by name evaluation, where you substitute the arguments unevaluated into the body. So basically the terms are what I showed you before, and the stack is this structure. So it's like an empty stack, or it's an argument which is appended to another stack in such a way that like the types align, basically. Since we only have one connective here, the implication, so you only have like this stack for implications, or an empty stack. So basically this is essentially like a list, but with more types to make sure that we've not written anything funky. Then the state, as I said, was just like a tuple. Again, this is basically a tuple. Like record is just a data structure with one constructor and a bunch of elements. So we have now two elements: a term of some context G and A, and the stack of some G and A, and B is basically like the answer thing. It's what we should get at the end. Then the step, so we just have like, if we have these simplified KRIVINE abstract machine, or CAM machine, then there are basically only two rules. So if you have an application of T to U and a stack S, then you throw the argument on the stack and look at the body. So you do a single step. And if you have a lambda and there is something on a stack, so this is basically a beta redex, a pattern for beta reduction, then you substitute this U inside of T. So basically this is a function that substitutes like this U for the occurrence of the first variable, so this one here, and then you remove this from the stack. And that's it. There's just two rules. And if there is anything else, you you stop and return the last thing that was valid. So this is how you reduce, how you write a KRIVINE abstract machine like with. So all these types that make sure kind of that we don't do anything funky, like kind of hold like this structure together. There's also a machine for call by value evaluation. It's slightly more complicated, and the only basically complication that there is additional thing in here. So stacks can hold not only like arguments for further evaluation, but it can also hold a body of an evaluated function. And the idea is here that if you have an application, then you do the same. You push the argument on the body, on the stack. And if you have a lambda and some argument to evaluate, that means the argument hasn't been evaluated. So since we're in the call by value mode, we should evaluate the argument first. So we switch to the evaluating the argument, and we throw the body onto the stack with this fun thing. And if we have a lambda fun, that means we've reduced the argument, and the only thing we could reduce it, because in the STLC the only values are lambdas. So this means this lambda is like the evaluated result of the argument. So we should substitute this argument into this T1, which was the definition of our function. So this is call by value. Yeah, so lambda calculus is also was said before is nice, but kind of limited in its scope. So what if, for example, we wanted something like effects? So like the most kind of general or very general class of effects is the so-called control effects, of which the example is exceptions. So before we had these 3 rules. So now we add like 2 more rules. So this is so-called lambda mu calculus. It was introduced by Parigot, I think this name pronounced in '92. And the idea is that it corresponds to classical logic. So lambda calculus corresponded to this minimal or intuitionistic or constructive logic. And this thing corresponds to classical logic. So these 3 rules are the same as before. And then there are 2 more things. There is this mu, and there is this pacification. So it's easier to explain this with the abstract machine, actually, what it does. But actually, the idea is that mu kind of saves the current stack. And this thing applies then. And then you have this extra bottom type. So this means like the function never returns. If you look at this, so you notice that we have like now these deltas. So this means we have kind of lists or multi-sequence. So we are back to this classical 2-sided sequence. So this means that this is our context or our free variables, and all of them must be true. So we should have all of these free variables, and one of these things should be true. That basically translates to we choose like one of these continuation to follow. Well, we cannot evaluate everything at once. We have to choose one of the remainder of the computation. So left is the variables and right are continuations. So what we can do with this, we can express classical laws like double negation. So if not A, so like usually you write negation as an implication to a false. So like if you have A, then like the universe is inconsistent, so it should be not A. So you have not A, you can get an A out of it. So this is usually not considered constructive. Or you have this Peirce law, or you have this contraposition, like if from not B follows not A, then from A follows B. So and this is how you would write like this in Idris. So you just add these 2 terms, and you add this bottom type to the mu thing. So then the mu thing kind of pops up the top continuation into the type, and the name thing kind of applies. So this element is like the index of the continuation, so it applies this continuation. So this is how we would write this Peirce law. And it's actually, the Peirce law is corresponding to what is known in programming as call CC, call with current continuation. So if you have a function that takes some kind of continuation, then call CC kind of saves the current context and passes it into that function. So you can write like very mind-boggling things with it. But the idea is that if you look at the type, so this call CC is basically just one lambda away from being a Peirce law. It's just instead of a lambda, you pass this function manually. But it's like the same thing. So yeah, as I said, it's easier kind of to explain like instead of like this logical explanation, it's easier to just show what the machine does. So now we have we switch back to the full machine and we ditch the types for now because it would be too busy to show everything. But basically, if you have like this untyped lambda mu calculus, so the environment is like the structure, the dictionary of all the terms or closures, but basically terms, and the list of stacks. So you have like double environment. And then, so these rules are kind of the same. If you have a variable, then these 2 lines basically tell you how to look up in the environment what you have. Lambda and application is the same. And so the mu thing then basically puts current stack on top of this stack environment. And the name thing looks up like in this environment and puts the stack into the current thing. So this is why you have this empty list corresponding to this bottom type. So this is the idea. Okay, so we have this simply type lambda calculus, and we have this lambda mu calculus. But what about the sequent calculus? How does it fit into this? So in this minimal propositional logic, let's go back to this intuitionistic logic for now. You had like these 3 rules, and you had these introduction and elimination. So you only worked, basically, you never constructed or destroyed something on the left-hand side. You never touched the context. You only worked on the type. So like you had this B here, you introduced this implication here, and you had this implication on the right side, you destroyed it on the right side. So the sequent calculus is the idea is that instead of like doing introduction and elimination, so instead of like saying, like putting everything in the term, you do so-called left and right introductions. So yeah, this is how it would translate if written down. So basically, this is how you would introduce something in the context, and this is how you introduce something as a type. And but still, you need some kind of notion of elimination, and this is called the so-called cut. So this is a very important thing in sequent calculus. This is like a so you can think of these two rules as kind of creating some kind of lemmas or detours in your proof, and this cut thing then removes it, kind of plugs your lemma and destroys like this indirection. It's like substituting. So, for example, if you have a function that calls another function, it kind of substitutes that function into that. So, and this process of reducing these cuts is called cut elimination, and it's a very important thing in proof theory. So basically, but the idea, like what does this correspond to in programming? So if you do this naively in this way, then this rule will cause you trouble. So just like we had in this lambda mu calculus, these context on the left and context on the right and some kind of type. So you can think of this as some kind of focus, or the thing that you currently focus on. So how you would do like a full sequent calculus for classical logic. So instead of having this bottom type, you split your sequence into three kinds. So you basically have like a context and the thing that you can focus on the left. So this is, you can think of this as some kind of consumer. The symmetrical situation on the right, so this is some kind of a producer. And then there's this command, which is like plugging consumer and producer together to start a computation. And then you have these 5 rules. So you can introduce like a variable on the left, a variable on the right. You can activate a command. So if you have a command which has like at least one focused thing, you kind of pull it out and make it back into, in this case, a consumer. And you can activate on the right. So you can take a computation and pull out the continuation out of it. And then you have a cut. So if you have a consumer and producers and their types match, so you can smash them together. And there are some technicalities about structural rules. So this basically corresponds to the fact that we should be using sets, but instead of sets, we use lists. So you have to have some additional properties that you can permute elements in the list and so on. But let's kind of skip it for now. So this is how you would write this in Idris. So you would write this like a 3 mutual data structure. So the command like only has a cut. So if there's a term with G gamma A delta and a co-term with gamma A delta, then you can run this computation. Then you have a variable, mu, covariable, and the mu tilde. So this whole thing is called like a Gensen LK calculus, or a mu tilde calculus, or a system L. There's lots of names for the system, but I think usually people nowadays just call it system L, not to have these funky letters. So what is this coterm? So coterm is just like a fancy name for these stacks or consumers or continuations. So it's all the same thing. And what is this mu and mu tildes? So mu basically, as in lambda mu calculus, it kind of names a continuation. So it's like saves the current continuation. And the mu tilde names a current term. So it's like a form of a lead binding. So this is like the core calculus, but if you look at it, then you can notice that there are actually no connectives in it. It's just like the administrative stuff, but it doesn't have even functions. So you cannot compute anything with it. All you can do with it is just rename continuations and terms, but you cannot run into anything with it. So how you would define things? Well, okay, let's basically what we said about coterms being consumers and stacks, then kind of reveals to us like very kind of important thing that since consumers are stacks and cuts are basically the machine configuration. So a sequent calculus is nothing but a formal model for an abstract machine. It's like a logical equivalent of an abstract machine. So if this is like a simplified abstract machine, and this is the simplified sequent calculus, then these things are the same. And the nice thing about this, then the reduction in sequent calculus is always tail recursive. You don't have to search through your term. You always have like on the top level a term and a stack, and you can immediately reduce something. So the sequent calculus, if you implement it, it's like out of the box. It's tail recursive and kind of low level, like closer to what the evaluation is doing. Okay, so how we would add like functions, deconstruct, for example, applications. So you don't have applications, right? Applications correspond to eliminations, and in sequent calculus you only have introductions. So what does the application do? Essentially, like if you look at the definition, for example, of KRIVINE machine, right? If you had an application, when you're reducing in the abstract machine, the application would push the arguments on the stack. And if you look at the rules of the sequent calculus, if you have like a mu And so you have like a consumer expecting some continuation, and you give it a continuation, and it just substitutes this stack into this command. So you can notice that basically this thing is just equivalent to this thing, right? It's well, it's like if you give e to this thing, then it will become this, right? It will just substitute e here. So you can take just this part and define the application as a thing that runs the current term and puts the u on the stack, and the remainder of the stack is something that you expect. So it like activates after putting the argument on the stack. And similarly, you can deconstruct lambdas. So you had this beta reduction, and in the machine form it looks like this. So if there was a lambda and something on the stack, then you reduce. So you can define lambdas as a sort of pattern matching on a stack. It's the thing that pops off the top continuation and takes your term and like makes this a suspended computation. So there's this new constructor that is like a pattern matching on a command. Similarly, you can just deconstruct LED bindings. So a LED binding is just a computation that activates some kind of input. Then you just put this t from the LED binding. So if you have, for example, let x equals t in some u that contains x. So this means that you take u, like activate it, so activate the term. So it would expect you to plug something into it, and you just plug t. And then you continue with this alpha continuation. So this is how you would write this, for example. This is just like the same thing in the Idris code. Yeah, and this is how you would write call.cc. So this is kind of complicated, but the base idea in here that call.cc kind of matches, so this is kind of a lambda, it matches on the current thing, then it produces some continuation, and this b is never used, it's just thrown away, and it just reuses this continuation twice. So this is like the essence of call.cc. It's you did something, you saved the state, and then you reuse the state. So this is why this alpha appears 2 times here. Okay, so how you would reduce this, for example, this core system L. So again, like a machine, so you have like a term on the left and a stack on the right. So if you have a mu and some command like activated by mu and a stack, you just substitute this stack inside of the body of this command. Symmetrically, like Sequent calculus is very symmetric. Like if you have a term and this activated stack, so it's something that expects a term, then you just substitute this term instead of this command. And if you have this lambda, then you just substitute 2 times. So you do some rearranging of the variables to make sure you don't do something funky like capture extra context or something like this. And then you substitute both the term and the continuation. But if you do this naively, then you have a problem. And the problem is like, what if you happen to have a term that has mu on the right and mu tilde on the left? Sorry, the other way around. So then you would have like some kind of a fight for control. So both of things are active and they all pull in their own direction. Like it's also called the critical pair. So basically, this corresponds to the idea that we have not defined a reduction strategy. So the simple way to kind of resolve this is always prefer do it on the right or on the left. So if you prefer do it always on the right, so always prefer do the co-term first or the stack first, this is nothing but lazy evaluation, just call by name, or call by co-value you could call it. So lazy is just a call by co-value. So you do it syntactically just by splitting these co-terms into mu tildes and co-values, but the idea is basically you force like the system to always reduce fully the continuation. Yeah, so now you have like commands, terms, co-terms, and co-values, and co-values is like a subclass of co-term. Dually, if you always force the system to go to the term, so to reduce by the term, then you split the terms into mu's and values, and then you call by value. So this is call by value. This is eager evaluation. So you've basically simply by noting that we have this non-determinism in this critical pair and kind of sticking to one strategy automatically gives us like this reduction strategies. Yeah, so you can go beyond it. This is like the very skeleton, but the idea, as I said, like if I wanted you to like remember one thing from this talk is basically that Sequent calculus is a logical framework for abstract machines. It's a logical framework. It's how you would logically, like have a logical foundation for writing, for example, an interpreter or a compiler. It's like not that you would have invent some kind of crazy thing and that just hope it works. No, it's just like some sound logical system which has been around for like almost 100 years now. And like if you translate it into the code with carefully, you just arrive at something that is verified. You don't even have to understand like these things like call-CC. You just, okay, this corresponds to this Peirce law. This is just like this logical rule. Just transcribe it into the code and bam, you have like this working continuation thing or a continuation running machine. So there are some more interesting things you can add on top. So one of these things, so when we did this dual reduction thing, we kind of forced the strategy into our into the structure of our thing. So we can also polarize the terms. That means like switching the strategy on the fly. So like annotating the types with lazy or strict. We can add more polarities. For example, we can do call by need by adding like even more of these polarities things. We can model some effects like quite easily by wrapping like this reduction thing in a monad. We can add more connectives like pairs and eithers and so on. We can generalize these connectives, so this would introduce dually both inductive data types and co-inductive co-data types like infinite structures, like infinitely running processes. We can add polymorphism, so move to the system F with this polymorphism like you've seen the talk today, but this gives us both universal and existential polymorphism for free, like because they're symmetric. And, whoops. Sorry, yeah, we can add dependent types. Like this is not being worked out in the literature fully, but if done, this would give us like this proof assistant like in Idris or something else that would allow you to reason both about finite and infinite computations. And here's some literature links, and yeah, I guess you can find the slides here, the code here. I will push a bit more things here. And we have this kind of webinar series, so it's in Russian only, where I kind of go through this stuff more slowly, like step by step, and we try to write like this simple compiler with lambda calculus just based on all these ideas. Okay, that's it, thanks.
Are there any questions?
So there was quite a lot of models, and you did a great job describing them from axiomatic point of view. Could you please briefly characterize them from like look and feel? Yeah, what's difference in applications? What model should I choose if I decide to use sequent calculus?
Well, yeah, as I said, basically, sequent calculus is like a logical foundation for a compiler or an interpreter. So the idea is that it's like not natural deduction is called natural for a reason. Like it's something that is kind of natural to how kind of humans think. Like they introduce things, they apply things to things. Like when you do mathematics, you apply an argument to a function. You don't think of that there's some machine that runs your functions. So yeah, so the idea is that you would have like a core syntax or like top syntax as some kind of lambda calculus, and then you would use sequent calculus as an intermediate representation. And you would, like just translating from natural deduction to sequent calculus, it amounts to like these compiler optimizations. Like if you take this LKQ calculus and try to actually write a translation from lambda calculus to this thing, then you would be forced to deal with values, and like to make long story short, this amounts to a transformation to ANF normal form for a compiler. So as I said, like you wouldn't probably want to write in this sequent calculus like as a top language. It's something that you would use like to have a formally verified compiler or something like this.
Okay. I think that was pretty obvious for everyone, right? So, here.
Yeah, thank you for your talk. There was quite a fast change from system F to sequent calculus, so I lost a bit of information. So we're moving from the lambda calculus with types to sequent calculus. So are there types in sequent calculus?
Yes. Everything is types. So for example, this LKQ thing, it has these like context for variables and context for continuation, and these things are populated with types. So all these indexes are types.
Okay, and so if there's types, so what about normalization in sequent calculus?
So normalization in sequent calculus is called cut elimination, and this program that this reduced thing is the implementation of cut elimination. So we are given a cut, and we are removing these top cuts one by one, layer by layer. So we eliminate the cuts.
I meant we guarantee to arrive at some result, or we can start.
Yes.
Strong normalization is.
Yes. Well, it's kind of equivalent to simplified lambda calculus. So we all because it has this cut elimination. It's like this is the nice thing, like to base this on logic, because there's like thousands, and maybe not thousands, but hundreds of these models in this logic or proof theory, and they like you already know, like people spend a huge amount of time like proving that if you take like this kind of formal system, then it has the property of cut elimination. So this means that it reduces. It doesn't get stuck. It has these type preservation and everything. This is what is nice about using this as a foundation.
Thank you.
Okay, we have time for one last question. Anyone? Okay, then that's it. Thanks for your talk, Alex.
Thank you.